Hi students, today we are going to see Unit 5 regarding gas turbine cycle. Gas turbine is a prime mover which converts the heat energy into mechanical energy. There are two types of gas turbine cycles. One is open cycle and another one is closed cycle. In open cycle gas turbine, every time the fresh atmospheric air is sucked by the compressor, and after compression it is sent to the combustion chamber where fuel is supplied, and fuel and the air both burns and we get the high pressure high temperature gas that is supplied to the gas turbine, which produces mechanical energy. That mechanical energy is transferred to the generator for producing the electricity, and the exhaust gas is let out to the atmosphere. This is the open cycle gas turbine. In the case of closed cycle gas turbine, the air which is entering the compressor is compressed and then it is sent to the combustion chamber, where as usual fuel is injected or supplied, and the fuel and the air both burns and produces high pressure high temperature gas, which is supplied to the gas turbine where mechanical energy is produced. That energy is supplied to the generator for producing electricity, and the exhaust gas leaving the gas turbine is sent to the pre-cooler where the enormous amount of heat present in the exhaust gas is removed by the pre-cooler, and then the gas is sent to the compressor. Again it is compressed and recirculated. In this case the same working substance is repeatedly used in the cycle, and hence we call this as a closed cycle. Now, in order to improve the efficiency of the gas turbine cycle, we are going to use some accessories. The first one is intercooler. The gas turbine cycle with the intercooler. This is a layout. Here, from the low pressure compressor, the air goes to the intercooler where the heat is rejected at constant pressure, and then it is again sent to the high pressure compressor where it is again compressed. Then this high pressure air goes to the combustion chamber where fuel is injected. Fuel in the air burns and produces the high pressure high temperature gas, which is supplied to the gas turbine, which produces mechanical energy. That mechanical energy is supplied to the generator. Now the exhaust gas from the gas turbine is sent to the pre-cooler where heat rejection takes place at constant pressure, and then the cooled gas again sent to the low pressure compressor for further cycle. Now the PV diagram of the gas turbine cycle with the intercooler is clearly shown, and we know here between 1 and 2 compression in the low pressure compressor, which is isentropic compression. So between 1 and 2 isentropic compression, between 2 and 3 constant pressure heat rejection in the intercooler. During heat rejection volume decreases, and then between 3 and 4 isentropic compression in the high pressure compressor. So between 3 and 4 pressure increases, and 4 and 5 it is constant pressure heat addition process in the combustion chamber. The constant pressure process is shown in the PV diagram by a horizontal line, and between 5 and 6 it is isentropic expansion in the gas turbine, so pressure falls during expansion, and 4 to 6 to 1 is constant pressure heat rejection process. That's what is shown by a horizontal line. This PV diagram is converted into a corresponding TS diagram. 1 to 2 is isentropic compression, so it is shown by a vertical line because during compression temperature rises in addition to pressure, and 2 to 3 is a constant pressure heat rejection, so during heat rejection temperature falls but the constant pressure looks like a curve, and 3 to 4 is isentropic compression. Again during compression temperature increases at constant entropy. 4 to 5 is a constant pressure heat addition, so during heat addition both entropy increases and also temperature increases, and 5 to 6 is isentropic expansion. During expansion pressure falls, also temperature falls, and 6 to 1 is constant pressure heat rejection process. So both the temperature and pressure, but the pressure is constant, but temperature falls, and hence entropy also decreases. Now Let us see how to find out the efficiency of the gas turbine cycle. Here efficiency is the ratio between output and input. The output we get is a network output and input is heat supplied. So here network output is turbine work minus compressor work. The turbine work is H5 minus H6. So we can show this in terms of temperature. We know specific enthalpy is a product of specific capacity at constant pressure and the corresponding temperature. So H5 is Cp into T5, H6 is Cp into T6. Similarly, compressor work we are going to find using the formula H2 minus H1 plus H4 minus H3. So compressor work is H2 minus H1 plus H4 minus H3. Again, we can bring this in terms of temperatures. H2 is Cp into T2, H1 is Cp into T1. Similarly, H4 is Cp into T4 and H3 is Cp into T3. Finally, the heat supplied at constant pressure is H5 minus H4 and nothing but Cp into T5 minus T4. Now we are going to see the gas turbine cycle with the reheater. So the air which is compressed in the compressor is sent to the combustion chamber where fuel is supplied. Air burns with the fuel and we get the high pressure, high temperature gas which is supplied to the high pressure turbine which does the work and produces mechanical energy, and the exhaust gas leaving the high pressure turbine is again sent to the reheater where it is heated again and then sent to the low pressure compressor. Again it produces mechanical energy, and here the generator, low pressure turbine, high pressure turbine and the compressor all are coupled in the same shaft. Now the exhaust gas leaving the low pressure turbine is sent to the pre-cooler, where heat is rejected from the exhaust gas at constant pressure and then again it is sent to the compressor for next cycle. And this is shown in the PV diagram. Between 1 and 2, compression in the compressor. Between 2 and 3, constant pressure heat addition in the combustion chamber. Between 3 and 4, isentropic expansion. Between 4 and 5, constant pressure heat addition in the reheater. Between 5 and 6, isentropic expansion. Between 6 and 1, constant pressure heat rejection in the pre-cooler. This PV diagram we can convert into TS diagram. So 1 to 2 is isentropic compression. So during compression, not only pressure rises, also temperature rises at constant entropy. 2 to 3 is a constant pressure heat addition. So pressure remains constant. It looks like a curve in TS diagram, but temperature rises. And between 3 and 4, it is isentropic expansion. So entropy remains constant. During expansion, pressure falls, also temperature decreases. And 4 to 5 is constant pressure heat addition in the reheater. So the temperature increases at constant pressure. Between 5 and 6, it is isentropic expansion. So at constant entropy, temperature falls because pressure falls during expansion. So 6 to 1 is a constant pressure heat rejection, which is shown in a curve. Between 6 and 1, temperature falls because of heat rejection. Now let us see how to find the efficiency. As usual, network output by heat supply. Network output is the difference between turbine work and compressor work. Now let's see how to find the turbine work. So turbine work WT, here there are two turbines. This is a high pressure turbine and this is a low pressure turbine. So the amount of work done by the high pressure turbine is H3 minus H4 and work done by the low pressure turbine is H5 minus H6. We can bring this in terms of temperature as Cp into T3 minus T4 and T5 minus T6. Similarly, we can find the compressor work input is here only single compressor, so H2 minus H1. In terms of temperature, Cp into T2 minus T1. The heat supplied here is two cases. The first case is the combustion chamber, second in the reheater. So the combustion chamber amount of heat added is H3 minus H2, in the reheater H5 minus H4. In terms of temperature, Cp into T3 minus T2 plus T5 minus T4. And the last case is gas turbine cycle with regenerator. In this case, the atmospheric air which is sucked inside the compressor is compressed and then it is sent to the combustion chamber. Before the air sent to the combustion chamber, it is preheated by utilizing the heat energy available in the exhaust gas. Now, after combustion, we get the high pressure, high temperature gas which is sent to the turbine. It does the work, produces mechanical energy and supplied to the generator, and the exhaust gas leaving the turbine is sent to the atmosphere. Before it is sent, the enormous amount of heat present in the exhaust gas is given to the compressed air leaving the compressor before it is entering inside the combustion chamber, because of which we get more thermal efficiency, also we get the fuel economy. And this is shown in the PV diagram. Between 1 and 2, isentropic compression. Between 2 and 3, constant pressure heat addition in the regenerator. Between 3 and 4, constant pressure heat addition in the combustion chamber. Between 4 and 5, isentropic expansion. Between 5 to 6, constant pressure heat rejection. The point 6 and 1 are joined by hidden line because it is an open cycle. And similarly, the same thing is converted into a TS diagram. 1 to 2 is isentropic compression. So at constant entropy, temperature rises because during compression pressure also rises. 2 to 4 is a constant pressure heat addition. So constant pressure looks like a curve in the TS diagram. So we get like this. And 4 to 5 is isentropic expansion at constant entropy. And 5 to 6 is constant pressure heat rejection. Similarly, the formula to find the efficiency is network output by heat supplied. Network output is turbine work minus compressor work. Now we are going to see turbine work, how to find. The turbine work is H4 minus H5 and compressor work is H2 minus H1 and heat supplied is H4 minus H2. Similarly, you can show that in terms of temperature as T4 minus T5, T2 minus T1 and T4 minus T2. Finally, we are going to club all the accessories in the same system in order to increase the efficiency. So this is gas turbine cycle with the intercooler, reheater and regenerator. So the atmospheric air is entering inside the low pressure compressor, which is getting compressed and then it is sent to the intercooler where the heat is rejected at constant pressure. Then it is sent to the high pressure compressor where the air is further compressed. Now this high pressure air goes to the combustion chamber. Before it is entering the combustion chamber, this high pressure air is preheated by utilizing the heat present in the exhaust gas. Now this preheated air enters the combustion chamber where we supply the fuel. This fuel and the air burns and produces high pressure, high temperature gas, and this gas is first sent to the high pressure turbine where it does its job, and the exhaust gas leaving the high pressure turbine is again heated in the reheater. Then this exhaust gas sent to the low pressure compressor where it does its job, and then this exhaust gas is let out to the atmosphere. Before it is sent to the atmosphere, it is sent to the regenerator where heat exchange takes place. So the enormous amount of heat present in the exhaust gas is given to the high pressure air which is leaving the high pressure compressor before it is sent to the combustion chamber. This is shown in the PV diagram. So between 1 and 2, compression in the low pressure compressor. Between 2 and 3, constant pressure heat rejection. During heat rejection, volume decreases. 3 to 4 is high compression in the high pressure compressor. 4 to 5, constant pressure heat addition in the regenerator. 5 to 6, constant pressure heat addition in the combustion chamber. 6 to 7, isentropic expansion in the high pressure turbine. 7 to 8, constant pressure heat addition in the reheater. 8 to 9, it is isentropic expansion, and 9 to 10, it is a constant pressure heat rejection. The same thing is converted into a TS diagram. 1 to 2 is isentropic compression. During compression, both the pressure and temperature rises, and 2 to 3 is a constant pressure heat rejection. When we reject the heat, not only temperature falls, also entropy falls. 3 to 4, isentropic compression. 4 to 6 is constant pressure heat addition. 4 to 5 is heat addition in the regenerator. 5 to 6 is heat addition in the combustion chamber. 6 to 7 isentropic expansion, 7 to 8 heat addition in the reheater at constant pressure, 8 to 9 isentropic expansion in the low pressure turbine, 9 to 10 is heat rejection in the regenerator. This is shown by hidden line because it is an open cycle. Now, efficiency formula is net work output divided by heat supplied. As usual, net work output is the difference between turbine work and compression work. And here there are two turbines and two compressors. Therefore, the total work output of the turbine is H6 minus H7 plus H8 minus H9. So, H6 minus H7 plus H8 minus H9. This we can show in terms of temperatures by Cp into T6 minus T7 plus T8 minus T9. Similarly, the total work input required to run the compressors are H2 minus H1 plus H4 minus H3. H2 minus H1 plus H4 minus H3. This we can show in terms of temperatures as Cp into T2 minus T1 plus T4 minus T3. Similarly, the total heat supplied here is the sum of heat supplied in the combustion chamber, regenerator, and also the reheater. So the combustion chamber heat supplied is H6 minus H4 plus H8 minus H7. So H8 minus H7 is regenerator. So we get T6 minus T4 plus T8 minus T7. Thank you.